Here are some practice problems to help us determine A, whether it's SN1 or SN2, B, the product of the reaction, and C, the mechanism of the reaction. So let's look at this first one here. We have a primary substrate. We have a good nucleophile. We have a good leaving group. And we have polar aprotic solvent. So aprotic, primary, those are our two main indications that this will proceed via SN2, and thus there's no intermediate, there's no cation formed. The nucleophilic attack and the loss of leaving group happen at the same time. And so we can do that just adding a couple of lone pairs on the I. Of course, there are 4 of them. We don't need all of them. We just need 1. And we show the backside attack on the carbon and the loss of the bromine. And that gets us to this compound. And the sodium is just a spectator ion. It ponies on up to the bromide in this case. So it's the primary and the aprotic solvent that helps us decide that it's SN2, and thus it's just this simple 2-arrow push. Looking at the second problem, we have a tertiary substrate. So right off the bat, we're thinking that it's SN1, because we know that SN2 mechanisms do not happen very readily, if at all, with a tertiary. We have a protic solvent. Acetic acid has the OH. We have a decent nucleophile, which doesn't really help us make a case, and we have a good leaving group, which also doesn't really help us decide. These are both sort of essential for both of the mechanisms. So we're going to predict that it's primarily SN1 because of the tertiary and the protic solvent. And so, of course, the first step in an SN1 mechanism is loss of the leaving group. We're going to make a planar cation here. We've got our leaving group, we've got the chloride, and we have, of course, the sodium acetate and the solvent that can be used in this case. And so now we're going to react this cation. It's a great electrophile. Every time we make a cation, I want you to think that is a great electrophile. And so now we're going to do the nucleophilic attack. There's no reason to rearrange this cation. It's already tertiary. And then we'll draw this, and that's the end. This is not a stereocenter, so I don't need to specify R or S or plus minus. It's not a stereocenter, so attack on either side of this planar cation will give us the same structure. So this is not a stereocenter. Okay, moving on to another one here. So here we have a tosylate, OTS, on a wedge. This is a secondary substrate. We have DMSO. We know that that is aprotic. And if you don't remember what DMSO looks like that. And we have a good nucleophile, and we have a very good leaving group. So it's the secondary that can tell us really the reaction could go either way, SN1 or SN2, but it's the DMSO that really helps us decide for SN2. And so we can start that off with our nucleophile, the methanethiol anion here. And we perform our standard SN1 arrow push, which is the nucleophilic attack and the loss of leaving group in the same action. This is a stereocenter right here, so we want to show that we've inverted that stereocenter, and so all we have to do is take the leaving group was on the wedge, we're going to put our nucleophile on the dash. And then we have OTS right here, and we have sodium along for the ride. It doesn't really play a role here. And so we have inversion here. That's the only enantiomer that forms, or at least that one forms in, say, 95 or 99% purity. So we get inversion here. Okay, let's look at the second on this page. We again have a secondary substrate. In fact, it's the same substrate, so we know we have a great leaving group. In this case, we have a protic solvent, and we have a poor nucleophile. So both of these, protic solvent, poor nucleophile, lead us to SN1. Remember that the nucleophile doesn't really play a role in the rate of an SN1 reaction, and thus we can use a poor nucleophile, we can use a good nucleophile. The rate will be the same. So the protic solvent will help us to favor the SN1 mechanism, which has that intermediate cation. It's more stable in a protic solvent. And so we can show this arrow push, which is the loss of leaving group. And actually I can do nucleophilic attack and loss of leaving group up there. We can keep track of these arrows if we want to. And so that gets us to this secondary cation, not as stable as a tertiary. Can we rearrange it? Whenever we produce a secondary cation, we should ask ourselves, can this undergo rearrangement? In this case, it cannot. We could make a tertiary primary there, or another secondary there. So it's not worth rearranging this. So now we should take our solvent, which is also the poor nucleophile, and react it with this cation. So the cation is so reactive, it will react with just about anything that's handy. So here's the nucleophilic attack. The solvent is handy. It can react, and we get this structure here. You might stop here, but in fact that's not the whole thing that attacked our cation. All of this should come along. There's no reason that the H came off yet. So the H is still there. So now we have almost the product. We have essentially the protonated product. And here is where we use one of our sort of optional proton transfer steps. We need to get rid of this extra hydrogen. How did we know to do that? Well, we took our nucleophile, circled in blue here, we attacked it, and now we have this extra thing. The product will never be charged. So we can also know that. And if you ever make a charged product, you've got a problem. So how do we get rid of this H? Well, what base is present? We have OTS minus. That's not a really good base, and that's because it's such a good leaving group. If it were a great strong base, it really wouldn't be a good leaving group. We also have plenty of ethanol around. Remember, ethanol is the solvent, so there is tons of ethanol around. Let's use the ethanol as a weak base and show this proton transfer step. And then we get to here. And in this case, I think we do have a stereocenter that we formed. And so maybe we want to indicate that we've formed both enantiomers, maybe not in a 50-50 ratio, but maybe 45-55. Alternatively, we could draw both enantiomers. And it's probably more correct. It takes a little longer to draw both. But that will save you some issues down the road if there were, say, let's make another stereocenter here. How do we do that? Say there was this cyano group here. And it would play no role in the reaction other than being just some other stuff on our substrate. So now what do I have? I don't have a mixture of enantiomers anymore. Can you see that? We've created a mixture of diastereomers. Get my pen back here. So that's where just simply writing plus minus might trip you up. If we had this cyanide on from the beginning and you wrote plus minus right here, you would not be correct. We don't make a mixture of enantiomers. We make a mixture of diastereomers because this stereocenter remained as a dash the entire time. It did not get changed at all during this reaction. And so here we'd create a pair of diastereomers because we've inverted just the one of these stereocenters, or at least we've racemized that single stereocenter.